Thank you very much for agreeing to present our society, Richard.
Yes, thank you. Would you like me to start now?
Yes.
Yes.
Please.
Okay. Well, thank you for asking me. Right. So this is a talk, an expanded version of a brief talk I gave late last year with some research I'm doing with these two collaborators here. So Hannah is the person who's done most of the work here. And it's on the issue of what kind of structure can we find in language use in the words of the lexicon. What kind of systematicity can we find there? So let's go on to the first slide. And so what we're talking about here is the idea that words that sound the same tend to mean the same. So most of us are aware that there are little pockets in the lexicon, like with the word sneeze, where there are lots of other words like sneeze, snore, snout, snozzle, sneer, snot, sniffle. Words that all have to do with the nose, but start with sn. So people have understood those have been around. They're just little groups of those, and there are historic kind of etymological stories to tell about that. These are just little pockets of the lexicon. So what we're talking about here is something bigger, something broader. And so let's have a look at how we work this out. So on this slide, I'll just be describing how to do this. So we want to have the spoken form of words. We want to specify their phonology on the left here. And then we want to specify the meaning of those words on the right. And we want to see if there's any kind of connection, any kind of statistical connection, correlation between them. So here we go. This is just a very small scale example. So ordinarily you'd be doing with this with a few hundred words, perhaps up to a couple of thousand words. I'll speak about that later. So this is just the toy example, and I'm doing this in English just to explain how to do it. The language we were working on was Korean. We're still looking at that. Korean is a really interesting language to look at for reasons I'll explain later, but the orthography of Korean is really especially interesting. So we've got these four words here in this toy example: dog and cat and sneeze and walk, the word walk. And these are the phonemic transcriptions of them. These are the meanings of them here: a dog, a cat, and walking and sneezing. And what we want to do is to see how the relationship obtains between those two things. So what we're going to do to start with is we're going to say we're interested in the distance of everything to everything else. So the distance from dog to walk, from dog to sneeze, from dog to cat. And from cat to dog, cat to walk, cat to sneeze. So it's a distance of everything to everything else. So if you have a large lexicon, that's a lot of, that's really a lot of distances there to work out. So let's just look how we do this. It's fairly straightforward with phonology. So these are the phonemes here, the k, a, and t. Phonologists have done a lot of the work for us. They've generally specified something like 12 different features which refer to the place in the mouth where the sound is made. It might be the tongue, the ridge at the back of the teeth. It might be the soft palate. So those are the places of articulation, and it might they also specify things in terms of the manner of articulation. So whether it's a stop where the airflow stops, like a k or a d, or if it's a vowel, if it's a fricative, where like s or sh, where there's some vibration occurring. So as I say, there's about 12 of these, and we can specify the distance between the transcription of the word dog and the transcription of cat just by specifying the number of changes at the level of features that we need to make to turn the word the word dog into the word cat. And so each of these things would have to be changed. The dirt would have to change to a k. The two of them are both stops, so it's a smaller number of things. And you just count the number of features needed to change the one word into the other one. And so that gives us the distance, all of the distances here. I should ask, can you see the cursor here? Yeah, okay, so that gives us all the distances there. And we want to do the same thing here for meanings. This is a bit trickier. A more intuitive way to do it is using a thing called WordNet that has been around from George Miller for about 35 years now, I think, where WordNet is a big handcrafted structure on the web. You can see it on the web. It's a kind of blend of a thesaurus and a dictionary where you can specify things like dog in terms of the concepts that are like it, the concepts it subsumes. So you have a big tree structure, and you can work out the distance between dog and cat in terms of they're both mammals, things of that sort. You can calculate things like the actual amount of shared structure. So that gives us something that we can call the a kind of intuitive semantic distance between dog and cat and dog and sneeze. It's intuitive because the whole structure of the WordNet was just handcrafted. We didn't do that. We did a more quantitative measure. We used something called latent semantic analysis, which again has been around since the 1980s. And this involves taking a really large corpus. These days from the web, you can get huge corpora of text. So there's the Google trillion word corpus, there's a lot of text out there. And what you can do is you can trade on the intuition that a word, the meaning of a word is defined by its use. And you can define the use of a word by the number, the different words it occurs close to in text. So if the word dog would occur close to feed and take the dog for a walk and things of that sort. So you don't need to specify all the other words, the proximity of all the other words to dog. You just choose something like a couple of hundred words, which are context words. They need to be fairly frequent words like hand and clock, and you can have the function words in there as well, like of and the. If you have really rare words like xylophone, then they're not going to occur next to dog or to cat mostly. So you want fairly frequent words. So you specify about 200 context words, and you look for just every occurrence of the word dog in a big corpus. And you look 5 words, say, to the left and 5 words to the right of each version, and of each occurrence of dog. And you say, which of the context words occurs in that window. And so you keep counting up the context words like that. And at the end of a lot of the corpus, you'll have acquired a list of 200 numbers, a number for each of the context words, which just tells you how frequently that context word, a word like hand or time, occurred next to dog. And just a moment's reflection will tell you if the words dog and cat are being used in a way that resembles each other. So we refer to dogs and to cats as being pets and things of that sort. The list of numbers for dog will tend to resemble the list of numbers for cat. So the list of numbers there we can call a vector, and it will be a lot, both of them will be a lot different to the word sneeze. So there are mathematical ways to represent the distance between two of the vectors, two of the distributions of context words, and you get a single number out of that. So at the point where you come to actually implement these measures, you discover there are lots of little choices to make and to think. Things like with just the phonology, which sounded easy, you have to say, if the words are different lengths, how much do we penalize that? So there are lots of little decisions to make. There are lots of different ways to measure the distances between things. And the big story here is you want the measures you use to behave fairly robustly. And so you want more or less the same outcomes if you use different measures for the distance between the spoken form. So during this research, we've investigated a few different measures, and they all behave more or less the same in a way, but some of them are better. And so what you do there is to go with the best ones. What we've got here is, so all of those numbers, what you get is a big list of numbers here. So the A's here are the distance between dog and walk for the form, the spoken form on the one side, for the meaning on this side. So all of these numbers correspond here, the distances. So the C one there is from cat to sneeze. And what we're interested in is the statistical relationship between the two lists. So the full-sized version of the calculation here, these lists are really, really long. So because it's the distance of each thing to all the rest of the things. So the big question is, what's the relation between them? If you think of the pattern of connectivity between the spoken forms there as a web, you've got this web here, and if you think of the same pattern of distances for the meanings, if you think of that in really in terms of a big web, if there was a very transparent kind of a relationship between them, the webs would be exactly the same shape, and the thing that would happen, the webs would be isomorphic, they'd be the same shape, and the correlation between the numbers would be 1. So at the other extreme, if we believed Ferdinand de Saussure that the spoken form of a word is completely arbitrary, that you could just as easily use the word sneeze to refer to the furry thing with 4 legs that you take for a walk. If you believed the meaning form, if the relationship between the two was completely arbitrary, the correlation here would be 0. So what is the correlation there? This work has been looked at a few years ago. These are all people that were here at one time or another. Some of them are still here, like Simon. And we did a previous version of this work a long time ago. The first author, Padraig, here led this work and did it all the right way in really a really mathematically sophisticated way. And what you find is the relationship isn't arbitrary. What we find in this paper here is that there is a significant correlation. It's very small, it's 0.065. It's very significant, but really small. When we did this for Korean, what we found was it was much bigger. It was twice as large, 0.13. Don't be misled by the 0 here. That just refers to one of the technicalities of the measures that we use. So there is a positive kind of a relationship. So words in Korean that sound the same tend to mean the same. Whether this is important, this is a lot larger. So this work has also been done for about 4 of the rest of the European languages. There's Spanish, German, French, Dutch. I think that's the other 4, and the numbers are all very small, all about the same as the one for English or smaller. All of them are really significant. So we'll be exploring this in the next few slides. Remember, if we square the number here, we get the percentage of all the variance that this accounts for. So squaring this, it's something like 1.6, I think. So you're only accounting for a very tiny 1% or so of the variance of all of the relationships between the form of words and the meaning of words. So it's not a dramatically large kind of systematicity, but it is still interesting and important. So let me move on now. So what I want to get across with this slide is that when we look at Korean and we slice it all up, we slice up the sample we use in different ways, what we find is this systematicity is in fact always there. So the sample we used in the original work on that last slide on Korean, we had 712 monosyllabic words. You want monosyllabic, you really need to use monosyllabic words in this kind of study, because you don't want morphemes in there like plurals and things that would, interestingly but artificially, sort of amplify things. So all of these are words like dog and cat and sneeze. It's not sneezed or sneezes. But you still find this statistical systematicity there. And we take out words that kind of have the same etymological root. So things of that sort. So what we did here, I'm not going to give the numbers here, but just to tell you what happens, we chop things up into the category that the words belong to. So Korean has been influenced for a long time by Chinese from the north, and there are lots of words in spoken Korean that are clearly of that kind of origin. So we divided them up into pure Korean words and the so-called Sino-Korean ones, the ones that came from China. And what you find is the systematicity is still there in the 2 halves. We took out just the syllabic constituents. So for the word cat, the onset is a k, the nucleus is the vowel, is an a, the coda is t, the rhyme is at, and so you can just put a wildcard in for all the rest of the word there, and you find it still works. So there's still a relationship between all of the words that just start k. It's a small one, but it's still there. We divided things up into nouns and verbs, modifiers as well. It's still there. We looked at a smaller group now of words where the sound of the word gives you some clue as to the meaning, and things are significant there. Even in a much smaller group of loan words, there's a systematicity there, which is really surprising. We divided the 712 up into different frequency strata, and it's only the rarest words where the systematicity dips down into levels of correlation which turn out not to be statistically significant. So this is a really pervasive thing. So all the slices of the Korean lexicon show this significant, well, all but the last of these ones here. So what's going on here? One of the things we did, which was really the reason we were looking at this, was we wanted to try something completely new. So the other work has been done in English a while ago, but this is a new thing now. I think looking at my email just before I gave this talk, I haven't had time to read it yet, but I got an email from Hannah that I think the article is in the journal now, sorry, or it's on the way. So that's Stop Press News there. That's good. I think she says that. I didn't have time to read it, but we'll see. So the Korean alphabet is really interesting because it was produced by the king at the time with a little committee of people, and they worked on it for about 10 years. And you'd think, oh, if you want to mess things up, get a committee to do it. But this works really, really well. So Korean orthography is fantastic. It's very, very transparent. The letters of the alphabet, and we're dealing with about 26 of them here, they're designed to, well, in the case of the consonants, look like, or to give you clues about position of the tongue and the airflow and things of that sort. The vowels are a little more philosophically motivated, to do with the sun and the moon and things of that sort, I think. I'm not the expert on that, though. So we wanted to ask the same question. If we took the orthographic form, just letters, and we took the canonical pronunciation, so for D, it would be D. Well, in the English example, if it was the letter D, it would be D. If it was letter M, it would be M. So these are the pronunciations which you teach kids first. So if you're using the phonics approach to reading, you want to teach them the pronunciation of all of the letters, and these are the ones you start with. So the examples I've used here are Korean ones. This is a M here, and there's some suspicion that this is to do with the mouth. This is H, this is D, this is S. Again, the example here is just really a toy example. And so we wanted to do the same thing again. We wanted the distance of each thing, each of the letters here, to each of the rest of the letters. So that's the visual distance. So the thing we're wanting to answer, is there something special about this that means that somehow this would be the most appropriate thing to use for a M? Could we have just switched over this thing and this thing, and it would be just as good? So we want to get those distances. We want the distances here. We've seen these before. These are straightforward. We just use the number of edits to the feature description of M that you need to change to get to H, or to get to D, or to get to S. So all of that's straightforward. The visual distance here is a bit more challenging. We used something here called Hausdorff distance, which is a very computational approach. It's essentially based on the overlap between the pixels in the drawing here and the drawing here. So the letter for M, the letter for H, to what extent do the pixels overlap? And there are lots of little assumptions you have to make about the size of the letter, the positioning of the letter. Towards the end of the talk, I'm going to suggest a distance which is better than that, I think, which we've yet to explore. But this gives you an accurate distance. We chose Hausdorff distance because we wanted to apply the the whole calculation here to different fonts. So we thought perhaps this font would be better than that font. So we wanted something really precise. In the history of people looking at orthography, chiefly for the Roman alphabet, people have speculated about downstrokes and curves, so things at the level of the feature like that. We wanted something more fine-grained so that we could compare fonts. So this is one we used, so that gives us, as before, all the distances, and it gives us the two corresponding lots of distances between the spoken distances on the left, the visual distances here, and we want to know what the actual correlation looks like. So it's pretty big here. This is large. This is the font here, the particular font. It worked for really for all of the fonts. This was about the best one though. So if we square this, we're up to something like 14% of all of the variance here. So this is good. This really feels like this would kick in. So Patrick Monaghan, with the work on the spoken form of English words, has shown that in that last paper I referred to, that the words that have the greatest contribution to the systematicity are the ones you learn earliest. And so he believes that the existence of the systematicity in the spoken form of the language is a bit of a help to children trying to learn the language. So going back to the spoken, to the written form, to letters, this really does start to say we could ask questions. If you're using the phonics approach to teach children to read, to teach them the sound of each of the letters, and we start with the canonical pronunciations, would we be better to start learning m or learning b, or start with the vowels? If we learn m to start with, then is there a particular one that we should learn next? So these are empirical questions. It's quite hard to think your way into this because the first investigation we did with lots and lots of words was a big corpus. This corpus, so the number of the letters here is small. There are 26 here. So this is a very small example, and the systematicity you get, I think, is really quite changeable, quite labile. And so there's a lot of further work to look at that. But it does raise this issue: can we have a more scientifically informed approach to phonics? Can we look at the substructure of phonics? That's that slide. So this is new stuff. We've just put this into a journal, possibly what Hannah was referring to as that paper, but so, okay, we'll see. So what's going on here? I'm going to try and explain why the systematicity is there and why it's so apparently pervasive, however you slice up the lexicon. So this is just words we'll look at here. So this long-tailed distribution is what the world looks like. This distribution is all over the real world. So if you said, so what we've got here in the y-axis is the frequency with which words occur, or it could be the frequency with which things occur. If you asked me, what do the trees of Scotland look like? I would say, well, there's one tree that's really frequent. It really occurs all over the place. It's the Sitka spruce, and that would be right at the top here. So the Sitka spruce would be the first of the rank of trees here. The next most common tree is probably, I don't know, it might be a birch tree. So that would be the next point here, and the birch tree would be there. There's lots and lots of them. And then the rarity of trees falls off really quickly. And so these are the frequent trees here. Then there's this long tail of really rare trees that they only have in the botanics and things of that sort. You find distributions like this if you said, if you were to take a gas and say, what's the distribution of the speed of the molecules of that gas? Some of them are really extremely energetic. They're moving really fast, and then there's a big trail off like that. So a long tail. If you look at words, there's a group of words that are really frequent. And so if you look at text, there's something like 140, 150 words that account for half of all text. That's the green group here. Then there's a lot of other words. So somebody like me would perhaps be using, say, in speech, 2,000 words, for life. Perhaps for text, I'd be looking at 20,000 different words, and perhaps all the words I could recognize but not really use much might be something like 70,000 words. Again, it depends how you define word. But so when we look at this, we find if you look at a corpus of transcribed speech, the most frequent word is the filled pause, that's the way you use it. Let me think of another example. The other example is have, but you're using to keep the turn open. You're using it to tell the listener I'm still speaking. All of that sort of thing. So there's a lot of ers. Then you have a lot of function words like have and get, the word the and of, and so these are the really the really frequent words. I'll just close this screen here because my screensaver is distracting me. If you look at the next most frequent words, they trail off a bit with words like walk and talk, and then the rarer words like rail and test and claim, and then a long tail of really weirder words like mace and trove that you don't really use much. So a few high frequency words at the top of the graph and a long tail of low frequency words. Let's look at what this means for that correlation between the spoken form of a word and the meaning of a word. What you have, these very frequent words are shorter, and there's a really clear intuition here that we want these to be short because we're using them all the time. You know, if you have a word like the, and if you look at that, if you tape some speech, if you record some speech and then you put that speech up on a screen and you say, and you'll find a great big, if you're looking at a representation of speech on the screen with frequency on the y-axis and time across here, you get a big zigzag like that. And if you say, find me the time where the word the occurs, and you're listening to little excerpts of that speech, you find that a word like the, as in I took the dog for a walk, it's very difficult to splice out just that bit of time where it's the word the. It's very short and it's merged with the word dog and the word took. I took dog for a walk. It's hardly there. You know, you have a very clear intuition. You've heard the word the. If I say I took the dog for a walk, and I have a very clear intuition, I've spoken the word dog, I took the dog for a walk, it's there. But if you look at where the articulators were, they're really, they just make a little gesture towards where the would be spoken, as it were, towards the dental fricative at the start of that, the z, and then the vowel which is a schwa. It's hardly there in speech. They're really short. So that process I've just referred to is known by phonologists as reduction. So you really, the tongue doesn't go to where it's supposed to be, or the lips don't go to where they're supposed to be. They just go to a brief nod, a brief approximation, and then they're sort of on to the next word, and the brain intuits what was meant. So these are easier words to pronounce. They don't have weird phonemes in, like j or z. If you look at when kids start to deploy the phoneme j in the word leisure, it's not till like 6, 7. So it's a hard thing. For the weirder words, you have these longer things with more consonant clusters like tr and rl here. They're longer words. They're kind of harder to say. So that's the kind of progression you get along the long tail distribution like that. If we now look for the meanings of words, and we looked at those context vectors. So remember, we're creating those context vectors. These are just toy examples. We're creating those context vectors looking at how often a word occurs in text. So if you have a rare word like mace, a rare word like prig or plump, things of that sort, rare words, they don't really occur much, and it's quite hard for them to accrue the context vectors that you're trying to count here. So the context vectors are all different from each other and really quite sparse. By the time you get up to the frequent words, the vectors are really full. There's lots of examples of them, and a similar kind of thing occurs if you look at homophones, like the word mug. The word mug can be a thing to drink out of. It can also mean to steal from somebody in the street, to mug them. It can also, it's a colloquial word for a face, for mug shots. It's also a colloquial word to revise for an exam, to mug up on an exam, to mug up an exam. So it's the same word, mug, being used for lots of different meanings. And the further you go up the frequency curve here, the more homophones you get. So it's a really weird thing occurring there. And so I think this is what explains the fact that there's a small level of systematicity, that the ease of saying a word, its shortness, the ease of reducing the vowel to schwa, just increases and increases as you go from the rare words to the frequent words, and the form of the context vectors will change as well, in that they'll get fuller and fuller and fuller. And so I think they're still all different, but I think that's really what's underlying the fact that the systematicity we find is really such a pervasive thing, which occurs in all of the slices of the lexicon. And so what I want to say here, coming to the end here, is what that means. We can think in terms of effort. If we're thinking of complex systems here, of everything interacting with everything else, like a pile of the grains of sand where all of them are kind of interacting distantly, and things can change. You know, if you just add a single grain of sand onto the top, occasionally a landslide happens, things will really change. So you can talk about a complex system like that as being in these states of poise. It's sort of, there's a kind of, there are kind of conditions of critical poise at different parts of the pile of sound, where different radical changes can occur. If we think of those really sparse words, in order to sustain a representation of one of the rare words where you don't have a lot of recorded instances in your head, where it refers to something very, very specific, like the word onyx. All I could tell you about that is it looks weird. It refers to a kind of black stone, I think, and it's possibly a hard stone. So that's a very sparse kind of representation. It might be used in jewelry. So trying to sustain that and to keep all of the rest of the complex, all the rest of the complex system there from interfering in that, that's lots of work. At the far end here, where everything is contributing, there's a very kind of robust understanding there of the word. Everything's contributing to the word, to the meaning of mug. I've got lots of examples. It's a really robust kind of representation where just where really just everything is active. So the intuition here is that as you go upwards to using the frequent words like have and got and mug, it's just easier. And so that correlation, I think, is what really underlies the fact that the systematicity we find is really pervasive. And I think that's working for the letters as well. So just going back to the letters, we use that weird Hausdorff distance. In the further work we want to do, I want to trade on the fact that it looks like work done is the really useful thing. And so what we want to do is we want to say, the letters you use a lot, you'd want them to be fairly straightforward to write. The letters which are hard to write, the letters you use lots, you'd want them to be harder. And so what we're going to do is just tell a person, I want you to write out the letter D 50 times on this sheet at this point, this point, this point, this point, this point. And so we just time them. We just time the amount of time it takes them to do that. And that would give us the amount of work used. So I think that's going to be the way to go. You won't be able to do different fonts or things of that sort. That's really a perceptual judgment. So we're going to move more to production. And that's sort of underwritten by the fact that when you look at a letter, what seems to be happening, you're activating somewhere at the top of the brain, in the middle, somewhere called Exner's area. So Exner was a psychologist in Germany in the 1890s, and he worked out that this was the bit of the brain you're using. And what you're probably doing to some extent when you stare at a letter is what we now think, the way we now think of perceiving, you're staring at that letter and thinking, how would I make that? So the labor involved in that is a useful thing, I think. So the conclusions, systematicity is really a pervasive thing in the use of a language. It's probably useful for language learning because the whole of the brain is like that, with topographic maps where they preserve structure. So the brain just works like that. And it's possibly something to do with the actual amount of wiring you need or things of that sort. Long tail distributions are the things to look at because the world is like that. The type of approach to psychology I use makes a lot of play with the idea of universal. In linguistics, we use that idea a lot. We talk about the universals that occur in all of the languages. In psychology, we use it a lot because we talk about things which we'd like to be true of all minds. The usage I'm doing, the usage of universal that I trade on is one where a universal can be a real thing as well. It's not just a sort of generalization. It's a real thing. And so I think the real thing we're looking at here, the material thing, is the work done, the actual labor, where the work can be the work in trying to write a letter, the work in trying to speak a phoneme, or the work in trying to sustain an informative structure of representation when lots of things would like to fire, but most of it has to be suppressed. So talking about work done is not a new thing. Someone called Zipf was looking at this a lot in language in the 40s. So that's where it's led us in this year. It's led us to looking at ideas that were around in the 40s. So on that happy note, that's progress for you. So okay, I'll finish now. We've just gone to 51 minutes, so lecture timing there. Right, thanks. So if anybody has questions about that, certainly happy to answer those. If you want to email me, I'm on the web, feel free, or we can have a one-to-one Zoom chat if you're interested in this stuff. That's all fine too. So that's a bit of an effort to listen to all of that. And it's okay if you don't have any immediate questions.